In this section of our relations module, we'll cover a couple ways of representing relations, and we'll use these to look at 4 different important properties of relations. So beginning with ways of representing relations, the first one is a matrix representation. And by the way, we're mostly talking right now about binary representations. We're assuming a 2D matrix here. So these can be represented as a binary matrix, and if the way that we write it is if the tuple is in the relation, we set the value to 1, and if it is not in the relation, we set the value to 0, right? And so see what I mean by that, right? We're going to look at R and R pre from the previous slide. And this is a representation of R. So remember, R was not a homogeneous relation, and we had a set L that was A, B, and C, and a set W that was all, ball, bat, and cat, right? And we've written them as the rows and columns. And what we're saying is that if a particular tuple is in that relation, I'm setting its coordinate to 1, and otherwise I'm setting it to 0. So I could translate this into the language of tuples, right, by writing A, comma, all is a tuple, right, because of this intersection here, and B, comma, ball, etc. Right, we can go through that way and write the whole thing out. You'll get what we saw on the previous slide, right? So this is another representation, and likewise we can do the same thing with R pre. Now remember, R pre was a homogeneous relation, so now you can see this set S is written out on both the rows and the columns. And I've just marked here every single time some tuple is in the relation, right? So you can see along this diagonal, I've marked all of the values 1, and that's because if you recall, because we have the empty string can always be W, everything was related to itself in that set. And then we have the other prefixes also marked 1. Another way of representing a relation that can be useful is through a directed graph, right, or a digraph. And in this representation, we take all of the elements in the set that we're working with, and we represent them as vertices in the graph. Right? So we'll do this in a minute, and then we place edges between the vertices if their corresponding tuple is in the relation. Right, so here's the example again using the same 2 relations. The first one, our non-homogeneous relation. I have my L here and my W, right? And they remain kind of separate, but I still can write all of the elements of L as a vertex, right? This is a vertex. And then all of the elements of W get written as a vertex. And then this is the part where I say I place an edge, right? That means I draw an arrow from one thing to another if the tuple is in the relation. And this is directed because we have A is related to all, A all, but remember tuples have order, so A all is not the same as all A, and in fact those are not related, right? So that would be not in the relation, and that's why the arrow goes this direction and it does not go back the other direction. Now, when we get to R pre, you'll see things look a little bit different, and that is because we have a homogeneous relation. So we no longer have this separation between our 2 sets that kind of keeps everything very orderly. We are just moving, from the set to itself. So you see things like self loops, and we have to kind of get a little more creative in how we represent it. Now, as you know, if you've seen a graph before, there's nothing particularly special about this arrangement. It's just that you are able to see all the vertices, but you can write the vertices however you want. We could write them all in a line if we wanted, but if we did that, then all of the arrows all the edges would cross each other in a more confusing way. So what you can see when you look at this, a convenient thing about this digraph representation is there's something very similar to, you remember that diagonal line of ones in our matrix representation. What we're seeing here, that 1 on the diagonal is represented by this self loop, right? That indicates that AA is related to AA, and likewise AB is related to AB. That's what this self loop means. And we can see very quickly that every one of these vertices has a self loop on it, and that's the same as seeing that there's a 1 in every column, or sorry, in every diagonal cell in the matrix. In the next few slides, we'll talk about what the name of that particular property is, the self-loop property or the diagonal one property, however you want to think of it right now. We'll name that, and we'll also talk about some other properties of special interest that'll give you some ideas of things that you might look for when you're seeing a representation of a relation that will tell you something about how that relation works. So the first thing is we'll talk about that self-loop property, or maybe a more descriptive way is the property of having every element related to itself. The technical term for this is that it is a reflexive property, and we can say that if we have some binary relation on S, it is reflexive if and only if R of XX is true for all X in X. So in other words, if and only if for every element in S, it is related to itself, right? And you've already seen this, but we'll give you an example here. We use R pre, and this is a reflexive relation, and the way that this shows up in a matrix, as we've already said, is that we see a diagonal column, or sorry, a diagonal sort of pattern of ones, right? And the way that it shows up in the digraph is all the self loops. So we've already covered that. All right, a few more though, interesting relations. A relation can also be symmetric, right? And the way that we define this is we say a relation R is symmetric if and only if R of x1, x2 implies R of x2, x1. I remember I made kind of a big deal out of how we had A related to all, but not the other way around. If it always is the case that when one element, say A, is related to B, that would always mean that B is related to A, that's when we can say, okay, then that's something special. That means this is a symmetric relation. So an example of a symmetric relation, we have a new relation I'm introducing here called RL, and that's a symmetric relation on this set S, which is similar to a set you've seen before, but a little different. And the way that this looks is the symmetry is something you can actually see in the matrix, right? I can see, okay, if I have a pair here on this side of the diagonal, I have to have it on the other side too. So in other words, what I'm saying there is if A is related to B, then it means that B has got to be, when I see B here, B has got to be related to A, right? A related to B means B is related to A. Now, the way this manifests when you're looking at a digraph is that every arrow out has to have a corresponding arrow that comes back in. So if A is related to B, B is related to A if it's symmetric. So that means every time I see this arrow one way, I get an arrow that comes back the other way, right? And that's true down here too. And if there is no arrow out, then we don't have to worry about it, right? So one thing that's very important to note here is that this property of relations is an if-then statement. This is an implication, which means only if x1 is related to x2 do I have to expect that x2 is related to x1. This doesn't mean that anything is ever related to anything else, right? There is no guarantee that x1 is related to x2 for anything in the relation, but if it is, then I have to see it come back, right? So if this were all zeros, that would be fine. That's still symmetric, right? But if there's a 1 somewhere. It has to be represented on the other side. Now, just as an exercise here, try pausing the video for a minute and thinking about this relation RL. What is a rule that you might give that characterizes this relation? Okay, so I've assumed you've paused and successfully characterized the relation. Come back, and I'll say there's more than one way to do this. But one thing you could say is, well, I noticed that my strings that have the same length, my string of length 1 is related to other strings of length 1, and strings of length 0 are related. And also, all strings are related to themselves, right? So this is a reflexive relation too, right? So this is about length, and we could write this and say, well, that means that the rule is x, y is in the relation if x, the length of x, is equal to the length of y, and that is what produces this graph when we're talking about this particular set. So the next important property that we're going to talk about is the antisymmetric property, and this is a property of relations, but you have to be careful because antisymmetric does not mean just not symmetric. It's not that everything that is not symmetric is antisymmetric. Perhaps fittingly, it is not quite just the opposite of symmetric, right? So what it means, we have to read the definition here. We'll sort of look at it very carefully. It means that if some element is related to another element, and so we would say, there's an arrow or that tuple is in the relation, and the element is related back to it, right? So x1 is related to x2, x2 is related back to x1. If both those things are true, it has to be the case that x1 is equal to x2. In no other case is this allowed. And so we can look at R pre on this set to see an example of this, right? On this new modified S that we created. And what you can see is if we have an element that is related to another element here, right? We have some 1 indicating that there's a tuple of some relation. Then there cannot be this other, the corresponding value has to be 0, except in the case where we're on the diagonal, right? And when we're on the diagonal, then this last condition is true, right? It's x1 is x2. So we do have the case that, epsilon is related to epsilon, and if you switch them, it's the same thing. And that's okay. That can be part of an antisymmetric relation because epsilon is equal to epsilon, right? But we can't have epsilon related to A and A equal to epsilon as long as epsilon and A are not the same thing. And that's what antisymmetric means. The way this looks in the digraph is a little bit more subtle, but essentially, if there's an arrow heading out from a vertex to another vertex, it cannot be heading back, right? Except for in the case where the arrow that's heading out and heading back is a self-loop. The last property we're going to look at now is the transitive property. And in some sense, this is one of the deeper properties, but the definition is, for some reasons, intuitive for people to understand. I think a lot of the time, that's what I find, is that students do not have as difficult time understanding this as, say, antisymmetric. So R is transitive if and only if, whenever x1 is related to x2 and x2 is related to x3, we have, that is also the case that x1 is related to x3. So that's the definition. So what does this look like? Well, both of our relations R pre and RL were transitive on this set S, and we'll show you what this looks like in a graph, right? So in the graph form, R pre, how do I find a transitive relation? What it means is if I have an arrow going from one node, my epsilon here, out to B, right? And I have an arrow going from B to BB, I know there must then be a shortcut arrow that also goes from epsilon to BB. And that is the case on every path that I follow, right? If I get these two paths, if I can get from A to AA, then I have to be able to also go directly. And you can see that's also the case here with RL, although in this case it's sort of trivial, right? Because everything connects back to itself. So that is all of the properties we're going to talk about, and what we're going to do with them is use them to describe special types of relations that are of particular importance to us. And the first of these, which is a very important kind of relation, is called an equivalence relation. Part C of this module, coming up next, is going to be devoted entirely to a discussion of equivalence relations. We'll talk about why they're important, and we'll look at some examples and try to show how you could maybe prove something is an equivalence relation.